So good evening, everyone, and thanks for joining me this Electrolyte. So this is Vinayaka. I work as a marketing at Decibels Lab, and today's session will be on mastering battery materials and components, the science behind next generation energy systems. And today's our warm host is Dr. Manjunath sir, who is a PhD holder. Let me give you a brief about his profile. Dr. Manjunath sir is an accomplished researcher and educator with over 21 years of academic experience and 16 years of research expertise in electrochemical energy storage and conversion systems. His work centered on the design of advanced battery materials, supercapacitors, solid-state electrolytes, and electrocatalysts for hydrogen generation, with applications spanning electric vehicles and sustainable energy technologies. He has authored 115 peer-reviewed publications, including 38 in Q1 journals, with a H index of 25 and 1,800 plus citations, and 4 patents, and several front cover features in leading side journals such as ACS Applied Electronic Materials, Energy and Fuels, and Chem, recognized among the world's top 2% scientists in 2023 by Stanford University. He has also received the ICT SGS Service Award, ACS and ECS Japan 2021, and multiple excellence awards for research and innovation. He is a member of the Royal Society of Chemistry UK, Electrochemical Society USA, and American Chemical Society USA. Manjunath sir actively contributes to advancing battery technologies, electrochemical modeling, and digital twinning for EV systems, making him a leading voice in the field of energy, materials, and electrochemistry. With this brief note about his profile, I warm welcome you, sir, Dr. Mugasa, for today's session.
Thank you, Vinayaka, for the nice introduction. Hi, everyone. Good evening. I'm very happy that during this weekend, many of you have make yourself free and join this bootcamp. And today's topic in this bootcamp is mastering battery materials and components, the science behind the next generation energy system. So in this next 45 minutes, 1 hour discussion, I'll be covering briefly, not in detail, because this is the content which can be taught for 15 to 20 hours, and I'll just briefly introduce you to these concepts. So this is actually second module of our the master course on battery materials characterization and digital twinning. In the first module, we cover the fundamentals of the electrochemistry, the theory and various the concepts, Nernst equation, thermodynamics, chemical kinetics, Butler-Homer equations, those aspects. And in the second unit, we'll be focusing on entirely on this battery materials, components, manufacturing, etc. So in that main course, so you can think that it's a trailer or a teaser as a movie in this 1 hour. So in this bootcamp, the mainly this talk is in the context of, as I mentioned, the Decibels Lab course, master course that is proposed, battery materials characterization and digital twinning. In this seminar, I'll be covering mainly on the components, battery components, the various cell formats in briefly, and inside that components, inside that cell formats, the anode, the material, cathode, various types of cathode materials, and the electrolytes, separator, and the binders, their importance, their role, etc. in the battery chemistry. And I will also touch upon the electrode manufacturing, assembly, and cell finishing. And then I'll also discuss about I'll introduce you briefly to thermal runaway, the degradation, etc. And I'll also touch upon some advanced advanced battery systems other than this lithium-ion battery. And finally, I'll take up the questions and answers based on today's discussions. So let us start with the battery, the basic the working first let us understand the working of battery by taking lithium cobalt oxide. So this is the widely used battery. It is there in all our laptops and mobile phones. And this is a rechargeable the battery which was proposed by Professor Gutenov. He was the awardee of Nobel Prize for this lithium ion battery invention. So why lithium? So why, if you take any battery chemistry, the lithium is used, or LFP or NMC, or you take LTO, it is having lithium. So why lithium? So what is the specialty of lithium? So we know that in the periodic table, those who studied chemistry in the 11th and 12th standard, hydrogen, helium, and the next element is lithium. So hydrogen is a gas, helium is also gas, but inert gas, it's not reactive. The next highly reactive solid material is lithium. So lithium is the lightest metal among all the elements in the periodic table. So we want the material to be light and reactive. So therefore, so we can expect more power density and energy density. And this is a metal which is having very high, very low reduction potential. Reduction potential means it can easily give away the electron. So, and high energy density because its weight is very less. And because of this light, not only lightweight, this is the third element in the periodic table. And if it oxidizes, it becomes a lithium ion. And the lithium ion size is very, very small. It's about 0.077 nanometer. So that small ion can be intercalated in the other matrix, metal oxides or graphite. So that is the beauty of that small size. That's why we use lithium. So what are the components basically used in this battery? The first one is the anode. So anode is one electrode where it undergo oxidation. Oxidation means what? It gives electron. It's a negative electrode. Generally, it is made up of copper coated with graphite. Graphite powder, it is represented by C6 and it has been coated on copper. So then we have another important component, that is the cathode. Cathode is a positive terminal. It is actually aluminum as a current collector, a thin foil, and the surface of that lithium cobalt oxide, a black colored the material similar to graphite, is being coated. So these are the two electrodes. So these two electrodes in which the lithium ion move between the two electrodes, so that it requires a medium for that ion to move between the electrodes. Therefore, we fill the electrolyte. Electrolyte is actually a solution. It's free from water. I'll tell you why that water, because lithium is highly reactive in moisture. So that's why we use non-aqueous electrolytes, especially organic electrolytes, the carbonate based, ethyl methyl carbonate, which are containing the lithium salts like NiPF6 or LiCl, LiBr, etc. So this solution provides the medium for the lithium ion to move between the cathode and anode and vice versa. Then we have to separate these two. See, since one anode is negative and cathode is positive, if you bring if they're in contact with each other, it leads to short circuit, right? So to prevent that, we are separating these two by another component of the battery, that is separator. So these are the main components of the battery. We should know about the structure, the chemical reactivity, etc. Because whatever the thermal runaway or the temperature increase, spike in the battery, the gas release, it's all because of the chemistry of these materials. So therefore, knowing about these materials is very, very important. So this bootcamp seminar is completely focused on these materials. So separator is actually a porous membrane, polypropylene film, a very thin film made up of polymer material. So which the insulator actually, it prevents anode and cathode. The role is to allow only the lithium ion to move between the electrodes. So these are the simple structure of a battery. Maybe if you take some other battery, maybe the components may be different. The anode, all the batteries will have anode, cathode, electrolyte, and separator. Okay. So this is how the battery, if you inside the battery, you can see here, this is the graphite anode, graphite, this is the copper foil coated with the graphite. Graphite is just, I just showed the layered structure. So this is a graphite is a, we have studied that it is the made up of layers of carbon. which are arranged in hexagonal network. So then we have a porous membrane, that is a separator, polymer based. You can see that these are the porous membranes. Okay, and then we have a aluminum. So aluminum is a cathode current conductor coated with lithium cobalt oxide cathode. So these are the layered materials. So these are like a slabs inside the crystal structure, and you can see in between they have layers where the lithium ion can be stored here. So this is the lithium ion, ions can be stored. The lithium ions are stored here. So then when you charge them, the lithium ions started moving in this direction from cathode to anode, and then they will intercalate between the layers of the graphite. Because as I mentioned, the lithium, the size is around 0.076 nanometer, and you can see that the interplanar distance in graphite is around 0.335 nanometer. So that lithium ion can easily be stored. Even after reducing, it becomes an atom. So that even the sizes are still less. So the ion and atom both can be stored between the layers. So that's why we use graphite. Okay, no other, this is the graphite is a carbon and stable material and conducting material. That's why we use that as a active material in anodes. So this is the structure. In the course, actually, we are going to discuss about the structure, the working, the why do we select copper as a current conductor, or aluminum as cathode, copper as anode, will be discussed in detail. And we will discuss the reactions also in detail in the main course. So the working is very simple. Initially, we make the battery by coating copper with graphite and aluminum with lithium cobalt oxide. Initially, they are stable. So then we are going to charge. So initially, we are going to charge the battery. Charging the battery means taking out electrons from this cobalt. Cobalt will be in +3 state, and it goes to cobalt +4 oxidation state. So by losing one electron. So electrons are pushed here, it becomes negative. So anode becomes negative. As a result of that, to balance that negative charge, the lithium ion from the lithium cobalt oxide, this lithium ion started moving in this, moving towards the graphite. So here we have electron, and here we have lithium ion. They form lithium atom in between the graphite. So this is becoming positive electro because it is losing the electron, and this is becoming negative, and this is becoming positive. By losing electron, this is becoming negative. So because of that, voltage increases. So one is becoming negative, other one is becoming positive, and it reaches about 80% of the lithium is being removed. So we can stop charging. So then it becomes active. So then we go for discharging the battery. So when you're discharging the battery, this has lost the lithium ion. So it wants that lithium ion back, and it is positively charged because we removed many electrons from that crystal lattice, that cobalt. Cobalt wants that electron back. So therefore, when you connect this to some load, some voltmeter, it started discharging spontaneously. It started discharging spontaneously from anode to cathode. So that is how we generate the energy. So this is the simple working of the battery. We need more time to understand this. So these are some of the reactions. Initially, we start with the copper coated with graphite and aluminum coated with lithium cobalt oxide. So when we charge, yeah, this is actually, sorry, this is, yeah. So this will undergo the lithium cobalt oxide. Initially, it will undergo oxidation during charging. Electrons are, see, the lithium is removed and electrons are being removed, and then they are pushed back to graphite. So you can see here, these lithium ions and X moles of lithium and X moles of electrons are removed from lithium cobalt oxide, and then they enter inside, and it becomes lithiated graphite. This is called lithiated graphite. So this becomes negative because we are adding electrons, and this becomes positive. So electrode. So this becomes cathode and anode during charging. So this is the overall reaction, and the same reaction is reversed during discharging. So during the main course, we will explain why this change in the oxidation number in detail, lithium, what is this X moles, how much percentage of the lithium can be removed, can we remove 100% lithium from this, or is there any challenges? So what are the challenges if you are to remove that lithium? If you remove 100% lithium, what happens to its crystal structure? So why there is a liberation of gas in this battery? Why lithium cobalt oxide is not used in electric vehicles, why it is restricted to only the mobile phones. Those things will be discussed in that main course. So this is just a glimpse about that. So with that background, let me go to the next aspects of the battery components. So battery is actually, if you, with respect to the weight percent, so the battery I mentioned, it's consisting of anode. The weight is about, for example, if it is 100 gram, the 14.5 gram is anode and 25.5 grams is cathode. And we have a current collector aluminum. Current collector is used along with cathode, and copper collector along with anode. So therefore, the electrode weight, so this much is the electrode weight. So total electrode weights, anode and cathode. So then we have electrolyte is about 11.2 grams out of 100 and 3.6 grams out of 100 gram. And you can see that in order to prevent that thermal runaway or to prevent the mechanical damage, all this component has to be covered with steel case, steel, so that weight is around 30%. So if you can come up with a very strong and lightweight material, still you can increase the power density of the battery. So this is also another drawback of this especially for the reduction of the power density. So I'll be covering all the components. Let me start with the various cell formats. I'll just pause at this stage. Am I audible? Vinayak, can you respond?
Yes, sir.
Yeah. So if anybody has any questions, you can ask me. So far, I have discussed. I'll just pause for 30 seconds. Okay, if there are no questions, okay, they may get the questions later after discussing the various aspects. So these batteries are designed in various formats, in the form of in the physical shapes. Some batteries are designed in cylindrical shape. Some companies they design this battery in a hard prismatic cell type or pouch type cell. Basically, the arrangement of the electrodes inside this cell are different. So in cylindrical battery, you can see the anode. This one is a copper coated graphite, and this is the lithium, whatever. If it is NMC battery, NMC coated aluminum, and we have a separator. So they are arranged one after another: cathode, separator, anode, separator, and they are rolled in the form of cylindrical shape. In case of cylindrical cell, in case of prismatic cell, same thing. We have a anode layer, and then this is the separator anode, and then we have a cathode, and all those, the bunch of them are arranged in a rectangular shape. And in case of pouch cell, they are actually sliced in a rectangular shape, each electrode, and they arrange one after another. You can see that this is the pouch cover, and then we have a anode layer, and then separator, and then cathode, and then separator. Again, one more bunch is placed. So like that, this is actually one stack. Like that, a number of stacks are arranged and then sandwiched in case of pouch cell. You can see here, this is the internal arrangement of the electrode. This is a stacking in case of pouch cell, and this is a flat binding in case of prismatic cell, and this is in case of cylindrical cell, wounding in cylindrical shape. And you can see the thickness of the current collectors. The copper is about 12 micrometer, and the aluminum is about 15 micrometer thin. And this is actually this is anode, and this is cathode. So anode, you can see the center one is a copper, and both the sides the graphite is steel coated. So the graphite coated is about 69 micrometer, 69 to 70 to 69 micrometer, And then you can see the aluminum current collector, both the sides that NCA and NMC material is being coated, and its thickness is about around 50 to 60, and this is 60 to 70. The graphite is about 60 to 70, and this 50 to 60. It varies from cell to cell. So then the separator is about 25 micrometer. So this is about the internal stacking. We will discuss about the thickness and how to optimize all these things, and what are the challenges, what are the plus minus advantages of cylindrical cell, prismatic cell, and stacked cell, and what are the in which electric vehicles they use. All those things will be discussed in detail in the main course. So when you tear down, when you open the cylindrical cell, this is actually the real scale cell, 18650 cylindrical cell. It is about 18 and 65 is the diameter, 0 is the cylindrical, 18 centimeter is the diameter, and 65 is the length. So this represents the dimension of the cell. So when this is the plastic case, when you open this, we have you can see that this is the copper foil. When you open the copper foil is an anode, and these layers are separated. This is actually a separator, and this anode, and this is cathode. So this is how they look actually. The real electrodes, this is how they look. Both the sides of you can see this is the copper foil coated with graphite on both sides, and this is a aluminum foil coated with this is actually aluminum. So this is aluminum foil coated with this is cathode. Sorry, this is anode. You can see this is the copper foil. Can you see this is the copper foil here? Copper foil color coated with the graphite, and the aluminum foil coated with that cathode material. And these two are separated by this polymeric membrane. Of course, the porosity is not visible, and it is for the naked eye. If you look at microscope, their pores are visible actually. So then the current collectors, we use copper as anode and aluminum as cathode. So this is copper for anode and aluminum for cathode. So why this? Why only copper? Why only aluminum? So why not if you swap? What happens if you use aluminum as anode? If you use aluminum as anode, what happens? Okay, of course we don't use. What happens if you use aluminum as anode? And what happens if copper is used as cathode? What happens? So, and what is the basis to select this? So these things in detail will be discussed in the main course. So all those things will be covered in that main course. Next, let us coming to the active material. So active materials are the materials which are actually involved in storage of lithium. Okay, the battery capacity depends on the quantity of the active material. Of course, the current collector, the main role, the current collector, copper and aluminum, is just giving electron and collecting electron, not only that one. The active material is the anode active material, the graphite, and the cathode active material. So whatever that NMC or LFP. So these are the materials, they store lithium ion. So the battery capacity mainly depends on this. And if you want to increase the capacity of that, you have to increase the quantity of this anode active material and cathode active material. And separator is not active material, it's inactive material. So when we are designing the battery, we have to consider that we have to try to fill maximum quantity of the anode and cathode, and try to reduce whatever that inactive materials like current collector, separator, and the aluminum and this one. You can see here. So this has higher energy density, and this is the two types of arrangement. The thickness of both of them is same. The overall thickness. Okay, the overall thickness for both of them is same. But this one, the first one, this is 1 and this is 2. The first battery gives high energy density, watt hour per kg, and the second one gives low energy density, less watt hour per kg. This is mainly because of, you can see here, the first case, there are few inactive layers. You can see the quantity of the graphite and the anode and cathode material is more, and the number of the current collectors and separators are less in this case. However, in this case, more. So therefore, while designing the battery, so we have to take care of all these things. So battery capacity depends. This is one of the reason about the reason that alters the battery capacity. So big cell means which is having more active material. Small cell means which is having less active material. So smaller the cell, lesser will be the capacity. So the bigger the cell containing more of active material, so more is the capacity. If you, of course, if you make the big cell with more of inactive layers, you cannot get more capacity. So next, coming to the first anode, component, important component of the battery, that is anode active material. So anode, mostly the graphite. Most of the electric vehicles, whatever that NFP battery or NMC battery, of course, these two are cathode materials. In most of the batteries, graphite, most of the lithium-ion batteries, the graphite is widely used, and it's represented by the symbol C. And now people are trying to use silicon as anode material, and people have also tried with for fast charging battery LTO. So LTO is Li4 Ti5O12 material. In place of graphite, they use LTO. So it is having high rate capability, but now one of the problem is that it is having very low cell voltage. So because of the low cell voltage, of course, the energy density will also be less. And lithium metal also people are trying, but lithium metal is highly reactive, and there are people are facing safety issues. You can see that these are the various characteristics of anode material LTO. It's actually heavier, the density is high, and the theoretical capacity is 175. And one of the advantage of LTO is you can see that the volume change when lithium, if you take out lithium and if you intercalate lithium, the volume change is very, very less. This is very, very important. So therefore, the battery life will be very, very high, and number of cycles you can see that greater than 10,000 times. But the energy density, so we are compromising with the energy density. It is just 100 watt hour per kg. Okay, so the full cell is also less. So the graphite, the density is less compared to LTO. Its theoretical capacity is 372. Okay, and the volume change, it's almost double the capacity of LTO, and the volume change is okay, 12% it is allowed, up to 15% volume expansion is allowed. That's why the graphite is being considered, and the cycle life is around 1000. As the energy density, you can see it is double of this. Okay, so because of the low voltage and less energy density, LTO is less preferred over graphite. If you want to have fast charging and high life, and of course LTO is very costly compared to graphite. So graphite is the cheapest material. LTO, because it is having 4 moles of lithium which are not used, which remains inert in that material. So titanium is also being used. So these elements are costlier than compared to graphite. So then you can see that silicon, why people are behind silicon, you can see the theoretical capacity is around 4,200. It's almost 10 times more than graphite. But one of the problem is that the volume expansion. So silicon expands around 300 times bigger than graphite. So therefore, the people are facing that volume expansion issue with silicon. If they can solve that, instead of taking 10 grams of graphite, they can just take 1 gram of silicon, because it is 10 times more capacity. So this is the research challenge about that volume expansion. Then lithium is also high, but the volume expansion is very high, and it catches fire easily, and it's highly reactive. So large scale production, it's also a lot of challenges. So this is the crystal structure, structures of graphite. Graphite is a layered structure. So as I showed, it can store lithium ion easily, and the LTO is a cubic spinel structure, Li4Ti5O12. You can see that the volume expansion is almost 1% here. This is around 12%. But the silicon, this is the size of the lithium, silicon. When lithium starts intercalating inside, you can see that the volume expansion is very big, volume expansion. So because of that, silicon is highly unstable. So it cannot give more cycle life. So of course, people generally the graphite. There are three types of graphite. So only the so this graphite is preferred for lithium-ion battery, and hard graphite is preferred for sodium-ion battery, because sodium ion cannot intercalate in this normal graphite because sodium ion is very big. So therefore, this hard graphite, this is how it look. So hard graphite is highly disordered, and it cannot be converted back to graphite. Such graphite is called non-graphitizable carbon. So graphite is preferred because of its layered structure and high theoretical capacity, and the interplanar spacing is matches with lithium. And you can see that silicon, you see for 4 silicon atoms, it can store 15 lithium ions. So this is the beauty. However, if you take graphite, 6 carbon atom can store 1 lithium. So 1 lithium means around 1 lithium is surrounded by 6 carbon atoms. You can see 4 silicon, almost 1 silicon atom can store 4 lithium. That's why its theoretical capacity is very, very high, almost 10 times more. So one of the challenge is that the volume expansion, and it forms an alloy. So in this, in the main video, I'll be discussing about the graphite preparation, manufacturing in large scale, what are the technique they've used, all those things will be discussed in the main course. And also the lithium intercalation mechanism, the stage-by-stage lithium intercalation mechanism, that volume expansion in case of silicon manufacturing, the detailed methods, the preparation and the challenges faced, all those things will be discussed. And even in LTO also, the preparation of LTO and the crystal structure, the intercalation mechanism will be discussed in the main course, or discussed in the main course. Okay. And if you look at the various, the cathode, LFP is widely used and NMC is widely used in the current EV market. LFP means this is lithium ferrophosphate, or NMC means is a nickel manganese cobalt oxide actually. So nickel manganese cobalt oxide. So all of them are having different crystal structure. So the LFP is actually orthorhombic olivine type structure, and NMC is actually layered structure, layered face-centered structure. And LiMn2O4 is also LMO battery. So LMO battery, it is spinal structure. The because of the change in the crystal structure, the path for the lithium ion it varies from crystal structure to crystal structure. In case of LFP, lithium ion can move only in one direction. So you can see this is the lithium ion, the yellow color, the balls, the small one. The lithium ion can only can move and intercalate and deintercalate only in this direction. That's why it is very stable. But in case of layered NMC battery, and graphite is also layered, so lithium ion can move in this direction also, or it can move in this direction also. So it's easy for the lithium ion to move because they get more freedom in 2 direction. So LMO is the fastest way, and the LTO is also similar to this. So in this crystal structure, lithium ion can move in all the 3 directions. It can come out in this direction, and also in this direction, or it can also intercalate in all the 3 directions. So because of the 3D empty channels, LTO is used as for fast charging batteries, fast charging. Of course, there are some limitations, not only this. So this is the various crystal structures provides various freedom, the empty channels for the lithium ions to intercalate and deintercalate. So you can see that this is one-dimensional crystal structures, and 2D, the lithium ion can move in this direction and move in this direction, and this is 3D. So this is how the crystal structure influences on the intercalation and deintercalation. In the main course, I have discussed in detail about the intercalation mechanisms with some videos, and what about the lithium ion sites and transition metal ion sites. In some active sites, lithium ion occupies octahedral, and in some crystal structure, for example, spinel LMO, it occupies tetrahedral structure. So because of that small size, the intercalation and deintercalation, it experiences more resistance, and this has less resistance. And because of that, the charging and discharging, if we take the lithium ion intercalation and deintercalation, we call it as a diffusion. If it experiences more resistance, it produces more heat energy that results in the liberation of gas. So all those things are covered. How does this crystal the sites of lithium influences on the uh, kinetics, and also the resistance, and the liberation of gas. All those things are discussed in detail by taking all the crystal structures. So the cathode, I have already explained by taking LCO. This is used in mobile phones and laptop. It's represented by LCO. LCO means lithium cobalt oxide. So because cobalt is very costly and also toxic, it cannot be used in large scale for EV vehicles. That's why that LCO, lithium cobalt oxide, they have replaced some percentage of cobalt by nickel, manganese, and cobalt. This is called NMC battery. NMC is modified form of LiCO2. So it is called, I have discussed about what is the meaning of that 0.18. Here we have XYZ. The XYZ is the various mole ratios of nickel, manganese, and cobalt. So we have NMC 811. It is about 0.8% of nickel, 1% of manganese, 0.1% of manganese, and 0.1% of cobalt. All of them, if you add, it should be 1%. X plus Y plus Z should be it should be equal to 1 mole percent. So like that, the NMC has been made with nickel rich, NMC 811 and NMC 622, that is 0.6% nickel, 0.2% cobalt, and 0.2% manganese. So their advantages and disadvantages are discussed, and how the safety issues are being addressed by doping nickel and manganese in place of cobalt, improved stability from LCO to NMC. Then NCA, nickel, cobalt, and aluminum doped LCO, that is called NCA. And LFP, this is completely different. It's a 1D intercalation cathode material. So are discussed. So this is the various percentage of each element in NMC 811. You can see it's actually the weight percent. So if you take Li 0.3, 0.3, and 0.33, it's actually 0.33, 0.33, it will be 1. So it is containing lithium about 7.2 grams. If it is around 100 gram of this cathode material, it contains about 7.2 grams of lithium. And manganese 19 gram, and nickel 20 gram, cobalt 20 gram. If you compare these are all the derivatives of LCO. So NMC 811, and this is NMC. This is not NMC 111, equal percentage of NMC, and this is nickel rich, and this is NMC 622, and this is NCA, nickel, cobalt, aluminum. And this is compared with LFP. LFP is cheap material. LFP battery is cheap compared to NMC is because of this lithium percentage. Actually, this is LiFeCO. So the lithium percentage is about almost 4.4 gram per 100 grams of the battery, but NMC is about 7.2 gram. Since lithium is costly, and in LFP, iron is also cheap. So iron is cheap and lithium percentage is less. That's why LFP battery is relatively lower cost compared to NMC. So the LFP is widely used in EV market because of its structural stability. NFC can remove 100% of lithium. So that is the beauty of this material in case of LFP. But NMC you can't remove. Lithium cobalt oxide, if you remove 100% lithium, the layered crystal structure they collapses. Okay, that is that is the drawback of that. But in this case, you can see here. So this is actually the lithium LiFePO4. If you start discharging if you start discharging the lithium ion, this is when it's fully charged. When it's fully charged, all the lithium is being removed, right? All the lithium is being removed. So these are the empty voids. So these are tetrahedral voids where lithium ion can go and sit in this direction. So this is in one phase. So this is one crystal, perfect crystal phase and stable. It's a single phase reason. Then when you start discharging means what? You're adding electron and you're adding lithium to this. You're adding electron and you're adding lithium to this. So then it started first initially the outermost surface started forming one phase and internal core will be in another phase. So therefore the structurally it is having two phase reason and it is stable. Slowly it is intercalating inside. And finally it ends up with another phase. So because of this, it provides a constant voltage in LFP. So you can see here the red color one corresponding to the constant voltage. So it is around 160. The specific capacity is around 160 milliampere hour per gram. So this is the reason. However, if you take NMC, the voltage curve will be like this. It's not flat. Okay, it steadily decreases in case of NMC. So this is because of the crystal structure. So I have discussed in detail the voltage variation, the voltage profile by taking lithium ion intercalation mechanism in various crystal structures. That is also addressed. So we have discussed about anode, cathode, and the next important part is the electrolyte. So electrolyte, of course, non-aqueous we have preferred in lithium because lithium reacts with water should not be used because lithium is violently reacts with moisture. The electrolyte is not a single component. It is made up of some liquids like solvent. Solvent is generally the carbonate-based organic ethyl carbonates or propylene carbonate, dimethyl carbonate. And in that solvents, lithium salts are being added. Lithium salts such as LiPF6 or LiBF4 and LiCl4. Li plus PF6 minus. It is ionizable. So in that solvent. So then they add some additives to increase its ionic conductivity. And then they are going to mix all of them, solvent plus salt plus additive, and you get the electrolyte. So you get this electrolyte. So of course it should be very clear and it should not be precipitate like this or it should not be suspension like this. So then such electrolytes should not be used. It should be a clear solution containing containing the lithium ions and additives. So what is the basis of choosing this solvent? So why these solvents? So because this electrolyte, is an organic liquid. Is a liquid, and we have an anode. Anode is graphite. Graphite, or you can say that copper, C6, this is aluminium. You can say LFP. These two are solid. So of course, the main role of anode is to give electron, right? So the anode role is to give electron. To give electron, the energy level should be high. So this is the electron rich. This is the energy level of the anode. And the cathode is to accept the electron. So if accept the electron means that the energy level should be low. So this is the acceptor level of cathode and this is the electron donor level. So then only it can easily donate electron. So electron can easily move from anode to cathode. But the electrolyte, the energy levels also matters here. So electrolyte energy levels where the electron is present in the outermost orbit, we call it as a HOMO level. highest occupied molecular orbital level, and the LUMO level where the energy level is empty, lowest unoccupied molecular orbital. So the one of the important criteria to choose the electrolyte solvent is that the HOMO level, you can see here the HOMO level where electrons are present in the electrolyte, the HOMO level should be lower than the cathode level. Lower than the cathode, sorry, the HOMO level should be lower. This should be lower than this level. Because otherwise, suppose for example, if it is above, so then this electrons present in the electrolyte will give electron to cathode, because cathode wants electrons, right? It will accept electron from electrolyte itself. Then no react, then it leads to explode, reaction, the gas formation reactions. All the electrolyte that you fill, it will decompose. That is one thing. The HOMO level should be below cathode energy level, and the empty energy level of the liquid electrolyte should be above the energy level of this anode energy level, that is mu E, that is a chemical potential, we call it as. What happens, for example, if the LUMO level is below the anode level or below or equal, then the electron present in the anode enters to the electrolyte, to LUMO level. So electrolyte will undergo reduction reaction. So then these electrons are not available to go to the cathode. So then no current. So that is one thing, and the electrolyte will undergo decomposition. So therefore, criteria for choosing the electrolyte LUMO or HOMO energy level is discussed in detail in the main course. It is just a glimpse. So the chemistry behind choosing the electrolyte with respect to their energy levels compared to anode and cathode are discussed in detail. So this is why we have compared the HOMO LUMO level of all these the electrolytes. These are all the carbonates. So this is the carbonate, and this ethyl carbonate and methyl carbonate. The various carbonates are being used as solvents in lithium battery electrolyte. Next, the very important concept is solid electrolyte interface, which is the thin film which is formed after packing the battery. After packing all the components, we are going to go for slow charging and slow discharging. That is called cell conditioning. During that, there is a formation of very thin film on the surface of the anode, but that is by reaction of lithium and some electrolyte initially, and forms an insoluble porous thin film that is called solid electrolyte interface. It's a thin film formation. It's like a membrane kind of thing, which acts as an interface between the electrolyte and that anode material. It is very important to form this. This has to be created. Otherwise, what happens? The lithium enters here during charging. It becomes a lithium metal. So lithium metal is highly reactive. If it is in contact with the electrolyte directly, it will chemically react. So therefore, to prevent that, we have to create SEI layer on the cathode. Similarly, the cathode electrolyte interface on the cathode. So the formation of this, their chemical characteristics, physical characteristics of all this SEI and CEI and their importance and how they have to be created, all those things are discussed in detail in the main course. So this is how the mechanism which is involved in the formation of SEI layer. It's a composition. First, lithium reacts with LiPF6 and the formation of LiF salt and lithium ethylene dicarbonate. The mechanism of the formation of the SEI is discussed. These are the various steps. So finally, it forms a thin layer, porous layer. So its composition is not uniform. From battery to battery, it varies. Even though if LFP battery is manufactured by different companies, so based on the cell conditioning technology they have used, its composition varies. So this composition varies. So this is very important concept, especially for understanding that electrochemical impedance spectroscopy. In the Nyquist plot, we get one spike corresponding to this SEI layer. So this gives an idea about the resistance that lithium ion has to cross this barrier, right? It experiences that resistance. So that will affect on battery capacity, battery energy, etc. So this is actually a very important concept. This has been covered in detail. Next, the another fourth component is a separator. Separator is an insulating polymeric material which is porous in nature. You can see with the naked eye, you will not be able to see the porous. But when you look at the scanning electron microscope image, you can clearly see the porous structure. Through this porous, the lithium ion intercalates and deintercalates from anode to cathode. You can clearly see this. So this is how this has to be designed. Of course, the Cell Guard is a very famous company. The pioneers, they manufacture this. It is basically made up of polymers, a non-polar material like polythene, polypropylene, and PVDF based material. PVDF is of course costly. For the large scale, they use polythene and polypropylene based the membranes. You can see these are the scanning electron microscope images they have designed by the Cell Guards company, and 2400 pp and 2500 pp polypropylene based, and you can see that the porous structures are completely different. It is about the porosity and the lithium ion and the electrolyte has to be, it should be able to wet the, it should not react chemically. It should allow only the ions to move between the anode and cathode. So I have discussed in detail about that. So then we have discussed about binders. So binders, of course, these are the other additives added when we are coating the anode or cathode materials. We add binders because binders, they have to hold that active material, maybe graphite or an MC, to the current connector. So they have to be whole. So this is, they acts like a gum. Of course, we have to add very small quantity, otherwise it increases the resistance. So this is the binder which holds the electrode particles and also the conductive additive, and it helps to coat. It increases the adherence of the coating material to the copper or aluminum. So generally about 90% of the active material is used, and 5% the conducting filler, and 5% of the binders are being used in case of anode. And in case of cathode, about 92 to 96% cathode material, 2 to 5% binder, and 2 to 5% of the conductive fillers. So electrode material, the slurry, is actually made up of three components: active material, binder, and conductive fillers. So their composition and the making of the electrode are discussed in detail in the main video. So then the last part of this is the battery cell manufacturing. Actually, we have discussed in detail about the various stages and what are the precautions to be taken. So of course, the battery manufacturing process consisting of three stages. The first one, after making the material, the anode, cathode, after collecting all the materials. So then we go for electrode manufacturing. It consists of dosing and mixing, coating, drying, dry coating. Dry coating is a new upcoming technology to prevent solvent-free coating. Then the importance of calendering, vacuum drying, all those are discussed. So after making the electrode, then slicing the electrode and making the cell assembly, the various types, pouch cell, cylindrical, and prismatic. So then filling the electrolyte. So then welding, tabbing. After that, we go for cell finishing. Cell finishing is a pre-treatment, and this is very important. Cell formation. During cell formation or cell conditioning, so we create SEI, solid electrolyte interface, or cathode electrolyte interface. And after that, there is a formation of gas. So that gas has to be removed. That is called degassing, then aging and testing. So these are the various stages. So that has been discussed step by step in detail in the main course. So this is an overall flow chart of this electrode manufacturing. Initially, we start with binder, solvent, conductive additive, and active material. All of them are mixed, and then made the slurry and tested the moisture content. If it is, it should be moisture free. Then the gas has been removed. So then we take the current collectors, maybe aluminum or copper. For aluminum, we use cathode slurry, and for copper, we use anode slurry. So then it is being coated, then tested for its coating, the surface coating, any porosity or everything is uniformly coated or not. So then it is subjected to calendering. Calendering is a process of pressing that coated material, making it uniform and highly adherent. So after that, it is subjected to bend, wind, and crease, scratch, various tests, and tested for its uh, the quality of the coating. So then it is sliced and vacuum dried. Moisture is again tested. So then they are all arranged. Separator, anode, cathode, like the depends on the whether it is required for pouch cell or cylindrical cell or prismatic cell. So it is all arranged. There are all discussed separately at the manufacturing level, various steps involved, and what is the procedure that they have followed has been discussed in detail. So after making the cell, they fill the electrolyte. So then they go for formation. Formation, they go for cyclic automated test, EAS, and hybrid power pulse charging, and cycling studies initially for the conditioning of the battery. So once the cell is finished, then they go for filtering the cell. Then they go for battery pack. So this is the overall manufacturing from active material to battery pack has been explained in detail in 2 to 3 hours of recording in the main course. So this is the overall process that I've discussed so far. Then I've also discussed about the Giga-factory lithium-ion battery manufacturing plant and the requirements. And for example, if you want to start the plant capacity of 30 gigawatt energy, and how do you calculate the cell energy required, number of cells, and how much quantity of lithium is required, nickel, manganese, and cobalt. So how many tons are required? For example, for 36 gigawatt factory, you require 2,924 tons of lithium is required, 19,783 tons of nickel is required. So for example, if it is NMC battery. So I have discussed how this cell inventory has been calculated, can be calculated, is discussed in my videos. So in the main course, you'll be able to get exposure about all this. So then I've also introduced about various advanced batteries, lithium sulfur, the upcoming technology, lithium air battery, and because of thermal runaway issue, people are working towards solid state battery. And this is one redox flow battery used for grid storage, and the sodium ion battery. So I've discussed about their work components, working mechanism, the constructions, the reactions, the challenging, etc. So this is the lithium air cell configuration where they use lithium as metal as one of the electrode material, and the membrane, a porous membrane, is used as a cathode. It's oxygen permeable membrane. So what are the challenges and the requirements for this cathode, and the reactions, the battery characteristics has been discussed in detail. So about all solid state battery, how the separator is being replaced, and the liquid electrolyte is being replaced by Nosicon type sodium ion super ion conductors. So everything is solid in this. The anode is solid, the cathode is solid, and the electrolyte is also solid. So no thermal runaway issue. So even there are some battery, even if they go to some 500, 600 degree, also they'll not catch fire. So the construction of this, the working mechanism are being discussed in detail. So then we have sodium ion battery. Sodium ion battery use similar to MCO and NMC, but instead of lithium salts, we take sodium and sodium salts. And instead of the graphite, they use hard graphite. So this is a disordered graphite they use. We have discussed about compared the battery characteristics of lithium cobalt oxide with sodium ion battery. Of course, sodium will give less lower voltage than LCO, but sodium is very cheap compared to lithium cobalt oxide. Sodium ion battery can give 2 to 3 volts, and this can go up to, lithium can go up to 3 to 3.5 to 4.5. So then I have discussed about thermal runaway issues, especially for battery management systems. The thermal runaway, it's because of the capacity degradation and then slight rise in temperature. Then the solid electrolyte interface that I have discussed, it started decomposing. So that leads to negative electrolyte reaction. So then separator decomposition, then there is a short circuit. So the main reason is it may be due to mechanical abuse, deformation of separator tearing. Then it leads to electric, it may be due to electric abuse because of dendrite formation. Dendrite is a growth of metallic elements between anode and cathode that leads to short circuiting. Then high temperature and collapse of separator. So finally, it leads to overheating and thermal runaway, and that heat dissipates from one cell to another cell. Then overall, the battery pack leads to fire explosion. So, so the reason for the degradation is the first, mainly it is because of the decomposition of SEI. So once the SEI starts decomposing, the lithium metal undergo dendrite formation. So it forms a metal. Then overcharging leads to lithium, more of lithium, and then this metallic lithium starts growing in the form of spikes, and it connects to the cathode. So when they connect, since lithium is a metal, when it forms a metallic conductor between anode and cathode, it leads to sparks short circuit. So that is one dendrite formation and SEI decomposition. Then copper ion dissolution and the current collector corrosion, then the binder degradation. So we have discussed about the reasons, various reasons for thermal runaway and battery degradation, taking all the components, current collector, binder, the graphite, SEI formation, the separator role, and the cathode, the manganese nickel leakage, the particle cracking. What is the reason for that, and how do you prevent? So all those things are discussed in detail in the main course. So you'll come across about all this. These things are very important in understanding while developing the BMS or simulating the material, about digital twinning. So what are the parameters that the inputs that you should give? You should take care of all these things. So then I've also covered the lithium ion battery. Once the beginning of the batteries are about 100%. If it reaches to 80%, then we go for we consider that as end of life. So it has to be go for we have to subject that to refurbishment. So refurbishment means LIBs can be refurbished and used for second life applications, maybe for another energy storage systems. So depending on usage, the refurbished LIBs can be utilized until the battery capacity fades to 50 to 60%. So then if they fail to give 50% of their SOH, so then we call it as the end of life. So then we have to go for recycling. So I have discussed the various types of the industry scale process used for recycling of the battery. So hydrometallurgy process, the one of the wet chemical method, they use various solvents to dissolve various components. Of course, it involves the physical cleaning. So then powdering and segregating all the components. So then the black mass, both cathode and anode material, the black mass is powdered and crushed and subjected to various acids and various strong alkali and acids, and they're subjected to leaching process. So like that, some metals are soluble in some acids, some metals they remain. The soluble metals are filtered out and then remained are subjected to some other solvent. So I have discussed in detail about the various steps used in industrial scale, the hydrometallurgy and also the pyrometallurgy, another method. It is used high temperature in the blast furnace, the presence of some reducing agents. Then electrometallurgy. So then, in addition to that, I have also discussed about biometallurgy and direct cleaning. So with this, the second unit, the module 2 covers all these aspects, starting from the various types of battery cells, prismatic, cylindrical, various fossil formats, and then the way anode materials, graphite, silicon, lithium, LTO, and cathodes, MCO and MC, LFP chemistry, there's crystal structure, and various combinations. Then the electrolytes, how do you make, what is the composition of that electrolytes? How do you choose based on the voltage window? And the separator characteristics, binders, fillers, etc. are covered. So then manufacturing stages, SEI, thermal runaway. So this is about the overall summary of this unit. It is just a trailer. I just touched only the surface level of this. If you come across, if you take that course, the main course, you will be study a lot of things from the chemistry perspective, which is actually very, very important for any digital twinning. If you want to design a digital twin of the anode, you should design the graphite structures, and graphite, the diameter is very important. The interplanar distance is very important. The lithium ion size is very important. So then only you can give inputs whether that anode is able to store the lithium, right? And the thickness of the current collector is very important. And why copper? So why not lithium? Understanding all those things are very important in developing the digital twin. And that is one thing. And in case of if you want to make the entire battery, the anode chemistry is different, the current collector chemistry is different, the electrolyte chemistry is different, and the polymer, the separator, that is a polymer chemistry, and the cathode, the inorganic chemistry. So it is having all the organic, inorganic, physical, all the chemistries are involved. So understanding some basics of that will help you to design a digital, the virtual component of this battery, and also the simulation, and then the modeling. So therefore, these things are very much essential for those who are aspiring to establish yourself in battery industry, electric vehicle technology. With this, I just conclude my discussion. So now I pause my discussion for the questions. Thank you. Vinayak?
Thank you, sir. Thank you for the session. Guys, we have already past 6:30. Any quick questions? If you have,
Yeah,
leave it in the
I
chat
did not
box.
notice. I had
Yeah.
put actually it was only the module 2 things that I have covered.
Thanks.
So I just audience, if you have any questions regarding this, I'm open to answer.
You can unmute yourself and ask the questions. Have given the permission to unmute. Anybody?
Good. Hello.
One by one.
Okay. My name is Oluwatoyin. Oh. Should I go ahead?
Yeah, please go ahead. Go ahead.
Okay. My name is Oluwatoyin.
Some cycles, like for the separator, like some of the anode metal will be sticking to the happen.
Sorry,
Thank
actually,
you so much for
voice is not clear.
But give me a second. Better you ask your questions in the chat box.
Please type your question in the chat box.
Yeah, after aging of the cell, like up to 80%, some of the anode material will start sticking to the separator. Like why does that happen?
That is because of the loss of the binder. So the binder that is used for the graphite, I had shown here, no? It is if it is detaching from the surface, it's because of the loss of the binder here. You can see my slides are visible, right?
Yes, 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 yes.
Yeah, this one. Because of this, if it assume that if it is detached from the copper, can copper collect electrons? Not, right? So because of that, some it loses the capacity. Even though that graphite can store more lithium, but it cannot take electron from the current collector. It can store lithium here, but it cannot take lithium electron. So because it is detached from the copper. That's why it loses from 100% to 80% or 80% to 50%.
Okay. Okay, sir. And also one more thing. In some cases, I have seen like there will be a like slight porous material on the cathode in the lower side. Like I think it might be a separator sticking to that. Because of that, it is forming a, like we will see a wave-like structure in the like, bottom side of the complete electrode cathode.
That is aluminum.
Okay.
I didn't get your question. Sorry.
Sir, like there will be a there will be formation like wave like formation in the cathode material like
That is
in
it
the end of
surface? Surface is
yeah,
being
yeah,
different.
yeah.
Is it in case of cylindrical cell or pouch or prismatic cell?
No, sir. It is in a cylindrical cell. Like
Okay.
recently, I have opened up one cylindrical cell and NCS cell. Like while I unrolling the material, like separator, cathode, and everything, like I can see some of the critical, like it is sticking to the cathode. Like it is because of the separator which sticks to the cathode, and I can see a weird structure in the bottom side of the cathode, sir.
Mainly that's sticking now when we are using a battery cylindrical cell for about 1000 or 1500 cycles. Because of so many times charge and discharge, the lot of heat has been dissipated, right? So because of that heat, that polymer based cell membrane, it has become softened. When you slightly melt that plastic, right, it becomes softened. So that may, because of that, it may.
We can see only in the like bottom side of the cathode, but we cannot see at the top side of the cathode.
Yeah, its main reason is you cannot predict where the heat is being dissipated in the battery. That is one of the challenging thing. Maybe it may be because of the heat is being released. When heat is being released, the gas is also being released because of the leakage of that nickel or manganese in the cathode. That oxygen gas is also being released. So because of that, expansion, that may be the reason for that wavy kind of thing, and also for that sticking, it may be because of the thermal. So that may be the answer, but practically you cannot say exactly in this position we can expect this, because that it all depends on manufacturing process. Even though if you follow all the steps,
I have seen in the multiple cells, and that too in the inner winding only I have seen, not like the outer windings.
it is mainly it's a physical phenomenon. Okay, it's mainly because of physical, because of the heat and that gas.
Okay, sir. Thank you for your.
Any more questions? You can leave it in the chat box. So some questions are there in the chat box. Please take it.
What was that? Somebody raised the.
Next.
Can you read Vinayak, that?
Oh, sure. No problem.
Okay. What is that?
Himanshu is asking from LinkedIn event, what is the reason to use AL for aluminum foil as cathode and CO foil, copper foil as anode?
Okay. So generally that anode we expect it should be having very high chemical potential, as I mentioned, because anode should be at a higher end because it has to give the electron, and the cathode should be at lower end because it has to collect the electron spontaneously, right? If you look at the chemical potential of copper and aluminum, the chemical potential of copper is higher than the aluminum. So the copper can only give electron. Aluminum can only give accept electron. If you use aluminum as an anode, if you look at the electrode potential, the oxidation potential, of aluminum is high than copper, because aluminum is around minus 1.3 volt and copper is plus 0.34 volt. It means that aluminum can give away electron easily than copper. So if you use aluminum as an anode along with graphite, then electrons are being released by aluminum only, not from the graphite. So during oxidation, during discharging, as a result, aluminum leads to corrosion after some time if you use it as an anode. So instead of that, you can forcibly make it as cathode, it remains stable. And copper being plus 0.34 volt, its internal, the chemical potential, 0.34, it is having a tendency to be in reduced form, metallic form. That is another reason. One is chemical potential and other one is their oxidation potential. I hope I answered your question. Himanshu, are you there?
He is joined from LinkedIn event, sir.
Okay.
I think he received it.
How can I measure the? How can measure the isolation in model and cell level? I think who is that? Arvind Jagan. Can you elaborate this question? Why is prismatic cell can be swelling? Swelling, it is mainly because of it is actually highly densely packed compared to pouch cell and other cylindrical. So because of there is no space for the gas, that's why we can expect more swelling in prismatic. To avoid prismatic cell swelling during storage or cycle. During storage means it has to be stored at very low capacity, SOH. State of charge, keep it at below 40%. If it is highly charged and stored, obviously battery tends to discharge spontaneously, and there is a chances of liberating gases. So better to be keep that prismatic cell with the SOH of for less than 40%. So that is a safer side if it is not being used for a long time. Cycle life means cycling means it has to be charged and discharged to the specified SOH. It should not go beyond that limit. Of course, overcharging leads to the liberation of gas. Over discharging leads to copper corrosion. Can I get the recorded about this session? Like I think
we'll be uploading the video on Monday.
This video will be uploaded. Okay. Thermal runaway related. Can you explain once? Okay. Thermal runaway. I have Arvind Jagan. Are you there?
Yes, sir, he is there.
Yeah. Okay. You want me to explain thermal runaway, and let me go back to that. Okay. So thermal runaway mainly it is because of the liberation of heat and the liberation of gas. That liberation of heat and liberation of gases leads to this cracking, SEI solid electrolyte interface formation, decomposition of SEI. If it decomposes, then some particles starts intercalating and spoils graphite structure. And the lithium metal I mentioned, when you are charging, keep on charging, the lithium metal is being accumulated here. Lithium metal. If there is no SEI, there is no SEI here. If there is no SEI, you can see here the lithium metal starts growing. So lithium metal, this is called lithium plating. So lithium plating and dendrite formation. So this leads to thermal, this leads to the internal connection between the anode and cathode. So when anode and cathode after charging, if they get connected, so it leads to short circuit. So suddenly all the charges which were stored forcibly in anode are pushed to cathode. So that because of the distortion, it destroys the separator and it leads to short circuit and the thermal fire catch is expected. So of course, this is one reason. SEI decomposition and dendrite formation. Dendrite formation takes place after over many cycles. So then, because of the resistance, if the binder decomposes, and if there is a contact between the graphite and copper, if there is a cracking, and if it is aluminum corrosion and contact loss between the aluminum and the cathode material, so then electron cannot go inside and outside. As a result, it increases the resistance inside. If the resistance increases, resistance means the resistance for the lithium ion to move. So it has to collide with other ion. That leads to increase in the temperature inside. So therefore, while manufacturing only, this has to be properly coated, designed, and while after manufacturing the cell formation and cell condition is very important, because that SEI has to be carefully formed. SEI and the cathode electrolyte interface has to be carefully formed on the surface of both anode and cathode. If it is formed too thick, then of course that is also problem. If it is formed too thin, then there is a chances of decomposition of the SEI with less size cycles. So this there is a the thermal runaway is mainly depending on the chemistry inside. So it may be due to separator, anode, or cathode. So all those things in detail explained in the main course. How much is the course fees? And I think it's available in the website. Can we use the combination of lithium and sodium inside a single cell to increase the voltage potential, but to keep the cost low? You cannot increase the voltage potential for lithium for using sodium, because sodium, the chemical, if you compare the chemical potential of lithium and sodium can give up to 2.8 volts maximum. So if you replace the lithium which can give up to 3.5 to 4.5 volt, if you replace lithium by sodium, you will reduce the voltage actually. You cannot increase the voltage potential. Of course, you can reduce the cost. The cost of the voltage will also be lost. The voltage loss, current capacity also losses. They are IP69 related rating. They provide what is, I didn't, okay. How can we prevent dendrite formation in battery? Dendrite formation, as I mentioned, it is because of overcharging. So when you overcharge, if you supply more electrons to the graphite anode, so more negative charge, right? So more negative charge means it will pulls more lithium from the cathode. So and lithium ion comes from the cathode and enters into anode, combined with electron, and it forms lithium metal. If you keep on charging more lithium, and the lithium atom combined with another lithium starts forming a metallic dendrites, and they start percolating, coming out from that SEI, destroys that separator, and finally it get connected with the cathode material, leads to short circuit. So overcharging, that's why whenever even our battery also, LCO battery, it's actually it should not be overcharged. So dendrite formation is mainly due to overcharging. So that has to be controlled by slow and charging below the specified SOH. We know that isolation. Okay, next, since the graphite have different arrangement of carbons, can you please explain how 6 atoms of carbon graphite, as you told during the session? I have actually, there is a 2 types of mechanism are there. In my main course, I have explained in detail about that stage 1, stage 2, and stage 3 and stage 4. So in that I have explained how that 1:6, that is a maximum capacity of the lithium we can push. Since the lithium is a hexagonal ring, right? Graphite is made up of hexagon ring. It means 6 carbon atoms made one hexagon ring. So in between that hexagon ring, the lithium atom can that void, we can call it as a void between the layers. That void is filled by one lithium atom. So based on that, it is mentioned that in the literature, 6 carbon is able to store one lithium. However, in case of silicon, it forms an alloy. So it forms an alloy, and because of that, it expands to 320%. How much battery is safely there, need to check. So it has to be monitored periodically. That's why the BMS is being used. BMS will tell you about the SOH, the battery, SOC and SOH, based by measuring the thermal behavior and the voltage behavior and the current behavior and the resistance behavior. So they have the sensors. BMS is embedded with these sensors. It will that BMS keep monitoring while using the battery and keep giving the details about the battery safety. What is the slurry thickness of LFP cell? So LFP cell means it's having a anode and cathode. Anode is a graphite, the copper coated with graphite, and aluminum coated with LiFePO4. As a LFP, I think are you talking about anode or cathode? Your question is not clear. Whether you are mentioning the cathode or anode, please specify that answer. Generally, it is around 50 to 60 micrometer. Even if you go for more thickness, you cannot intercalate the material. So that has to be optimized. It is in micrometer, around 50 to 70 micrometers, similar to that NMC. How was the working active cell balancing? So the active material has to be balanced. The quantity of active material, both anode and cathode, based on the capacity. So I think in my first module, where I have discussed in detail about the battery, the capacity calculations, calculations, where graphite is around 320 milliampere hour per gram, and LFP is around 120. So to balance the same capacity, first we calculate for per gram how much capacity, and accordingly we have to balance how much quantity has to be taken. So that is discussed in detail in my first module in this course. Of course, I have not touched those basics in this today's discussion. I'm Helen from engineering student. I'm doing research on batteries, and I wanted to fabricate a battery with the nickel oxide as cathode and zinc as anode. So how do I start if I am doing this with a college lab setup? So are you working on lithium ion based battery or zinc ion based battery? Please clarify your question. Ellen, since if it is a zinc ion battery, you can do it at your lab. If it is a lithium ion battery, you need to have specially designed glow box where it has to be carried out in an argon atmosphere with less than 1 ppm moisture. Zinc battery can be made with zinc sulfate as electrolyte, zinc as anode, and nickel oxide as a cathode. There are a lot of videos and literature is there. You people can refer that zinc ion battery. Are there any effect if we store the cell per battery pack in SOC 70 to 90%? Are there any? That depends on the battery. Actually, NMC is LFP is safe compared to NMC, because NMC, there are some reports that because of that cobalt present, cobalt leads to the liberation of oxygen that I have discussed in one of the video. Liberation of gas, if it is stored at very high percentage, 90% is high actually. This open circuit voltage, how can we calculate for SOC? That is discussed in my first module. I think I'll be taking, if required, one more boot camp on first module, and also the third module, that is on electrochemistry, electrochemical aspects, or the techniques I have discussed in that. About the voltage, I have almost 1 or 2 hours discussion in that. I hope I've answered all the questions which are appeared in the chat box. So if anybody has any question, please. Or else you can also mail me. So my Vinayak, you can share the email in the chat box. My email ID. If you have any questions, you guys can mail me. Since it is a weekend, I appreciate all the participants, joining. I thought of just 45 minutes to 1 hour, and it took almost half an hour extra. Sorry for that extra time. I hope all of you have enjoyed, and hopefully you guys can take the course. With this note, I'll be concluding my talk. Thank you all.
Thank you, sir. Thank you for the session.
Yeah, thank you. Bye.
And thank you everyone for joining in on the weekend and staying back till here.